quicksort. So we cannot complete this time. Next class, we may need to use the first half to complete the remaining part. All right. First, let's look at the motivation part. So this new sort, our main goal is emphasize overall performance. Overall performance, that means the average case efficiency. So we allow the bottleneck part, bottleneck, the worst case in big O of n squared. So we can tolerate that kind of worst case. But the overall efficiency, we want to make it as fast as possible. So when we design the algorithm, we need to use some special way to do it. Here, let us look at this design idea. So when we design it, we still use divide and conquer, but we want to do it different from the way we do it in merge sort. All right. Yeah. But the question, how to make the overall performance as fast as possible? Yeah. Because in your design, you just want to use a completely different way to do the divide and conquer. It's hard to control the overall efficiency, right? It is very hard to control that overall performance. Only after you find the solution, then you can do experiments to compare the overall efficiency. Okay. So here, when we design the algorithm, we just want to use a completely different method in order to get a new algorithm with different properties. All right. So here we need to, some of you may ask, because the worst case still very poor. Why you said you can tolerate this kind of worst case? The reason is simple. Because the probability to have this worst case is very slow. When we apply this overall very fast algorithm, we usually will apply it many times, large number of times. So then people look at the average case efficiency. A small number of worst cases, when you take the average, you will not get a bad average number. So with that into our consideration, so we feel we can tolerate that kind of worst case. All right. How to change the view? We need to do comparison. All right. We need to, recall how did we do the merge sort. So for the merge sort, divide and conquer, there are 3 steps: divide step, conquer step, and a combine step. In these 3 steps, the conquer step is automatic because by recursion. Conquer step, we do recursion to take care of this conquer step. It's automatic. But divide step and a combine step, then we need to use our special ideas here. For the merge sort, divide step is very fast because we split our data right in the middle. That is very fast. We don't need to do comparison, right? We just count number of elements, or we just work on the indices. That is very fast. So here we use big theta of 1. But the combine step, that's our merge operation. When we apply merge operation, we need to do this much work. Big theta of k. K means the data size. All right. The new idea, we want to change our focus. We want to get a completely different algorithm. So how about, because you can imagine it is impossible to make both divide step and conquer step both very fast, right? So it's a trade-off issue. If you make divide step very fast, then you have to do more work at the combine step. If you want to make the combine step very fast, you have to do a lot of work at the divide step. So our new idea, we want to make the combine step very fast, big theta of 1. But we are willing to do more work at the divide step, big theta of k. Because after we change the focus, the sort must be completely different from the previous one. So that's the way people try to find a different sort, then compare these two sorts. So which one has better, faster overall efficiency? All right. Yeah. Now question, how to make it happen? That's our design idea. We want to make it happen. The details, the implementation details, are very smart. So this method, the idea for our problem solving understanding, the idea is very useful. All right. The current, so here, Quicksort, right. So that we will look at the detail. All right, the question. When we start, let us start with the combine step first. How to make the combine step easy? To make divide step easy, it's very easy, right? You split the data right in the middle. That's all you need to do. Big theta of 1. But combine step. How do we make the combine step extremely fast? That looks non-trivial, right? That looks non-trivial. So when we start, we want to do a lot of analysis for this step. All right. How to make it very easy? So here, let's imagine almost do nothing in the combine step. When we combine, we do not do comparison. We do not do any comparison. We just put the two arrays together. Then the whole array automatically sorted. Each subarray, because after conquer, right? After conquer, each subarray is ordered. Then we put these two subarrays, these two ordered subarrays, back to back. Yeah. Connect them, join them, without any number of comparison, then the whole array is automatically ordered. That's the, our design goal. Part of our design goal. We want to achieve that effect. Yeah. All right. Look at the two subarrays. We want to see what property our data should have to allow us to have this property. When we combine them, we just do nothing. So we need to explore the special property on our data. All right. Yeah. Before conquer, these two subarrays, in general, not ordered, right? Before conquer. After divide, so here, some of you may want to ask how to divide them, right? Yeah. Let's delay it, the divide step. Yeah. Because let's work on the easy step first. Combine step easy. So we always work on the easier step first. Yeah. Not sorted, each one not sorted. After conquer, we do recursion. Then after conquer, so each subarray is sorted. Then, when we merge two sorted arrays, no comparison is needed. Can you imagine what special condition you want to impose on your data? The data has to follow some special requirement, right? Not arbitrary data. After you split, then you conquer each of them. When you put them together, you get the whole array automatically ordered. No, not arbitrary. So there must be some special condition there. So we want to find that condition. All right. Yeah. So after, so do nothing, right? So that condition is very important. Yeah. But it's not hard to see it. It is not hard to see it. Yeah. The condition is, look at this inequality. Yeah. The value of each element in the first subarray is smaller or equal to any value, the value of any element in the second subarray. A of I, you can choose any I in the first subarray, is less than or equal to B of J, you can choose any J in the second subarray. In other words, you can say the maximum of the first subarray is less than or equal to the minimum. Yeah? Because anyone, you can pick the maximum, right? In the first subarray. Second one, you can also pick any element in the array. You can pick the minimum of the second subarray. So the maximum of the first subarray should be less than or equal to the minimum of the second subarray. That's the requirement. If you make your data with this property, then when you combine them, you don't need to do any comparison. You don't need to do any comparison. Okay? All right. Yeah. But the question, I think most of you at this point, you will ask question like this. How to make it happen, right? It's hard to make it happen. Yeah. We agree if this property is achieved, then We don't worry about the combined step. We can get that big theta of one efficiency in our combined step. But the question is, how do we get this property from the divide step? The divide step. The main goal of divide step, make sure our data has this property. Yeah. All right. So when we move to the divide step, so we will solve this problem. All right. Yeah. So that's the most important step in this algorithm, divide step. Yeah. So the idea used here, very smart. Yeah. Although not too complicated. Not too complicated, yeah, but very smart. Yeah. All right, requirement here. So let's just, formulate. Try to, streamline our thinking a little bit. How to split the array into two subarrays, A subarray and a B subarray, such that A of I less than or equal to B of J. All right, yeah. When we do the split, we do not require that A subarray is ordered or B subarray ordered. We do not require that. So we only want to have this property. The order inside each subarray is not important because we will fix the order problem in our conquer step. Recursion conquer step. We can take care of that part. So in our divide step, we don't worry about the specific order properties in these two subarrays. All right, D.2, partitioning in quicksort. That most important step. Partitioning step. All right. Implement the divide step. Now we need to target that our special goal. This is our main goal. This inequality when we divide our data. At first, people may feel it's very hard to control our data in this way, right? Yeah. But we can do some special operation on our data to make it happen. Our original data does not have this property, and it is far away from this property. But we can do some special operations on our original data. At the end, we will get this property. All right. First, let's do our first try. Yeah. Our first try, we want to see, because first try usually not the best solution. The first try is, we just want to get this target, but we may not do it in the most efficient way. Yeah. First try, we do not know what is the best way to do it. Yeah. We just want to find one way to make it happen. Yeah. We may need to use too much resource in the first try. Yeah. But we achieve our goal. That's the bottom line. We achieve our goal. But we may need to use more than necessary computing resource to achieve this goal. Yeah. So let's do our first try. All right. How to split the original array to get this targeting property. All right. So let us imagine the result of our data splitting is these two subarrays. All right. And with these properties. Okay, all right. Yeah. Now we need to find some, relatively simple way to make it happen. Okay, all right. Yeah. There is some uncertainty regarding the sizes of A subarray, B subarray. We don't know how large is the A subarray and how large is the B subarray. That's one thing. Unknown. Yeah. All right, yeah. So if there is too much uncertainty, then we do not know how to get started. Yeah. So we need to, we need to find some, so let's work on this part. Yeah. Let's get some idea first. All right? Let's get some idea first. All right. Yeah. How to make it certain? How to make it certain? Yeah. It looks like the question is hard to answer. Yeah. All right. Let's dig a little deeper in this question. Yeah. Because we need a separator. We need something to separate these two subarrays. So there is a special concept here, some object we need to use to separate these two subarrays. Yeah. So that object is a special element to separate the two subarrays. Yeah. How to pick one special element that we could use to separate. After we separate these two, we have this property. So here you can see, you need to imagine there is some special object you need to use. All right. So here the key property of this separator element, this element must be in place, right? Yeah. This element must be in place. So this special element, you can determine its final location in this divide step. After the divide step, you put this special separator element in place. Yeah. All the other elements may not be in place, but at its left-hand side, left-hand side, right-hand side, two subarrays. Its left subarray and its right subarray, left subarray, the values, all the values of this left subarray, smaller or equal to some number, okay, some number. And its right subarray, all the elements, the values of all the elements are greater than some value. The value is, because this is an element. This element has a value, right? This element has some value. So the left subarray, the value should be less than or equal to the value of the separator element. For the right subarray, its value less than or equal to less than the arrow. Yeah, arrow should be this direction. Right hand side, the arrow should be in this direction, greater or equal to. then this special element is critical for this divide step. If we can determine the special element, then we can easily complete that divide step. All right. Next, determine boundary of two subarrays. Now we need to work on that boundary portion of these two subarrays. So let's look at there is a special element in between these two subarrays. P. Here we call it P element. Why we call it a P element? People give it a special name for this element called a pivot element. No, it is very important. Yeah, the pivot element. Yeah. So we need to find a P element, the pivot element. It is in place. This element, when you look at its value, it is in place. Okay? Yeah. Then, other than that, another property, A of I for all the elements in the left subarray must be less than or equal to P, and P less than or equal to the values of all the elements in its right subarray. If we can make it happen, then we complete the divide step. So at this point, you can see we have better understanding, right? Yeah. We addressed, or we, fixed a large part of the uncertainty, right? Yeah. But there is still some uncertain part. How do you determine that pivot element, right? Yeah. You don't know. You only know your goal. This is your goal. This is what you want to achieve. But you don't know how to achieve this goal. You need to do a lot of work. So our next round analysis, we want to work on the implementation part, details, to make it happen. Which element is used as the pivot? That's the critical question. Important question, right? Yeah, that's the important question we need to answer. We have freedom to choose. When we choose this pivot element, we have a lot of freedom to choose. But in a given array, you have no idea regarding the values in the array, right? You have no ideas. Which one is smaller, which one is larger, which one is in the middle, you don't know. You have no information. So under this assumption, no information about your data, which element you should choose as the pivot element? Let's answer that question. So the answer is, any element has an equal role in the array, no preference. Any element, the chance to be chosen as the pivot element is equal. That's fair, right? That assumption is fair. If you agree with this assumption, then when you choose the pivot element, it's very easy. Random selection, right? Yeah. No matter how you choose the pivot, it is almost equal. All right? You can random select one element in the array and make it the pivot. Yeah. So the problem is fixed. The result could be different, right? Sometimes you choose a good pivot. Sometimes you choose a bad pivot. That could happen. Yeah. We will see that. That big difference. The difference is big. Good pivot, bad pivot, the difference is very big. All right. No reason to favor any particular element. So random selection. Yeah. So we've fixed this selection problem. Pivot selection problem. We fix it easily. Random selection. All right. But next question. After we fix this random pivot selection problem, we have another technical problem we need to address here. Yeah. Yeah. Point position wise, yeah, because this random selection is regarding the values, right? Value wise, your selection is random. Yeah. But position wise, it's different, right? Yeah. The positions in the given array, they're quite different. Yeah. You have total n different positions. Some positions are more convenient than other positions, right? Yeah. So this time we need to understand the differences for the elements in different positions. All right. That means we need to select the best position for our pivot element. That's the meaning. Value, we don't worry. Yeah. Random selection, we can take it. But for the position, now we need to investigate, right? We need to do comparisons for the elements in all different positions. Yeah. So let's look at the next round analysis. This time, we focus on position information. Let's look at a typical position somewhere in the middle of this array. Yeah. Let's imagine if we put our pivot element in this position, what would happen? All right. Yeah. For a general random position you select somewhere in the middle of this array, yeah, think about your goal. You want to achieve the properties of these two inequalities, right? That's your goal. But the question, your original data, we can assume no such property, right? No such property. So you need to make it happen. You need to do some non-trivial work to make it happen. So what kind of work? So you need to manipulate the data. You need to move the elements around. You need to move the elements. If you do not move the elements, you can never get this property. So you need to move your elements around in this array. Changing the positions of some of the elements in this array. Okay? Yeah. So let's put that in our understanding. Try to understand this technical problem. Okay. All right. Definitely, so when you consider an arbitrary location in the array, the element in that position, in general, is not in place. Yeah? In general, it's not in place. Yeah. So if you make this your pivot, you need to move. Eventually, you need to move this element. Change it. Move it to a different location. Okay? Oh, yeah. Other than move this element, you also need to consider how to move other elements in other parts of the array. You need to consider how much work you need to do to move elements around. Okay? Yeah. Then you can see this element, the location of this is not convenient because it looks like it is a roadblock. When you move elements around, right? When you move elements from left side of this element to the right side of this, you always need to do a lot of position changing work, right? You always need to do position changing work. And you don't want to do that much work in this step. Yeah. So based on this understanding, you want to consider some special position such that that position would not block anything when you move other elements around. That position is special. It will not stand in the middle of other elements. Yeah. So that special position, you can see in this array, there are two special positions, the first position and the last position. Because only these two positions, they won't block moving other elements. No blocking effect. Okay? You can freely move all the other elements around without worry about any interference from these two positions. Very, very easy. So this analysis tells us these two positions are the best, most convenient positions for our pivot elements. So with this second round understanding, now we are very close to our destination of the device step. Yeah. Now we feel it's doable. Okay? Yeah. So after we build up this understanding, so the last round we can make it happen. We can do the manipulation to make it happen. All right. Now, so here, let me select the last position for the pivot element. Yeah. Some people like to select the first position. Yeah. No difference. Yeah. All right. Yeah. Here in my presentation, I choose the last position as the position for the pivot element. Then we imagine two subarrays, A subarray, B subarray. They should be arranged like this. Yeah. And with the desired properties. All right. Then we need to make this last step happen next. Okay? All right? Now let's fix this implementation part in partitioning. Yeah. Straightforward implementation. That's our first try. Yeah. So after we get a lot better understanding, now we are ready for this first round, first try implementation. All right. First try, we don't worry about the computing resource. We just want to, reach the goal. That's the most important thing. Yeah. How to reach that goal? We may need to use a lot of computing resource. Here, these two auxiliary arrays, that's the extra resource we need to use in our first try. All right? Now, when we start, let us, work on our data following a certain order. Scan the array from left to right in order, in its natural order. All right. Then, because we have two auxiliary arrays, so let us, put two empty arrays ready to store the two subarrays after the split. Two subarrays. Two auxiliary arrays. All right. We have plenty of space to use. Now, let's start the operation. When we take the first element in the original array, we compare it with the pivot element. If it is less than or equal to p, we drop it to the first destination array, auxiliary array. If the value of the current element is greater than p, strictly greater than p, then we drop it to the second auxiliary array in order, in the natural order. That's easy, right? Yeah. In this way, you can see after you finish the scanning from beginning to end, except to the last pivot element, then you get what you need. You get two subarrays. The values of the first subarray satisfies the first inequality, and the values of the second subarray has the second inequality property. So you make it happen. All right? You divide your data with the special property achieved. All right? Yeah. Yeah. All right. Next, yeah. So our first try, we make it happen. Yeah. Then we need to consider, is this solution acceptable? Is this solution good enough? Yeah. So our next round, we want to improve it. Because first one, we do not worry about the computing resource, right? So we may use more than necessary resource to make it happen. So our next round, we want to use the minimum amount of resource. We want to save the computing resource. So the question, is it possible we can do the same thing, partition, divide, do the same thing without using these two auxiliary arrays? If we can do it, then we can save a lot of computing resource. Storage locations. Here, that's the storage location. So we do not save comparisons. We still need to do the same number of comparisons, but we save a lot of storage resource. Yeah. So when we talk about computing resource, all right, so here, computing resource. There are two types. The first type, that's the primary resource. That's the, here. So most of the time, number of comparisons. Okay. Or in the general case, we can say number of basic operations. The general case, number of basic operations. Right? Yeah. The second type of resource, secondary. That's the storage. Storage locations. All right? Yeah. So primary, secondary, we know the primary is the more important than the secondary. Save in the primary resource is more important than save in the secondary resource. Yeah. But so our first round improvement, we work on the primary resource reduction. After that, the second round improvement, we work on the secondary resource reduction. Here, this place, so we work on the secondary resource reduction. Remove these two auxiliary arrays. We want to separate our data in two subarrays with the two desired inequalities without using that much storage space. Yeah. All right. How to make that happen? Yeah. You need some smart ideas here. Yeah. So here, definitely we need to use some extra space. You are allowed to use extra space here. Yeah. When you manipulate the data, you have to use, most of the time you have to use extra space. But we want to control the extra space used. We don't want to use too much extra space. So what do you mean extra here? With respect to what you mean extra? So we have the standard part, extra part. Standard part, we do not count as the extra space. So the standard part, that's the space. You need to use space to store input-output data, right? Input-output data. All right. But other than input-output data, you still need to use a little more space to store some temporary data, intermediate temporary data. So that part we need to control. Do not use too much extra space. All right? So now we need to consider the improvement part, how to eliminate auxiliary arrays. Yeah. All right, so all the main space we will use the space from the original array. That's the main part of it. Other than the main part of space, definitely we need to small number of extra storage locations. Small number of, a few, yeah, not too many. Yeah. All right. Then our data, yeah, we divide the precious space in our original array into several regions to characterize. Remember, organize data. How to organize data? Here, we need to do data organizing work. How do we organize our data? So we use some special regions. For example, S region, that means smaller or equal to that P. L region, larger than that P. The values in L region, larger than P. Yeah. I mean, just to, put them into different category. Yeah. Organize our data in different categories. Yeah. Then there is a U region that we use for unprocessed elements. Unprocessed. We haven't done comparisons. Yeah. So we will manage these three different regions to characterize our data. Yeah. If you can find an organized way to control these three regions, then you can divide your data with the targeting properties without using the auxiliary array. But you may need to use some small number of extra storage space locations. All right. Then, when we need to look at the working specifics. In A subarray, so that's the S region part, we need to grow the S region, right? When we add elements into this A subarray, we grow this S region. B subarray, we need to grow L region. At the beginning, they both empty. These two regions are both empty. So then, when we do the processing, we grow them. Yeah. Unprocessed, at the beginning, it's the whole array except the pivot. Yeah. Other than the pivot. So all the elements are in the U region. Yeah. But at the end, the U region is empty. All right. So now we are ready to do the partitioning. Yeah. So example. Yeah. So here I have about 5 minutes. So I think I have enough time to work on one concrete example to show you the working details. All right. So let's do the work. Concrete example. It is a small subarray. Simple as this one. Yeah. So let's do the scanning, processing, comparison, but we need to work very carefully, yeah, to control our data in different regions, different categories, in a well-organized way. Yeah. So let's look at the work in detail. Pivot element, the last one. Yeah, so we use different colors for elements in different categories. All right. U region in white color, unprocessed. All right. Then we need one extra space we use to swap the elements. Do swapping. All right. Here, let me run the comparison step by step here. When we start, both regions are empty. So we do our first comparison. Compare 2 and 4, and we know 2 is smaller than 4, so we put it in S region. Second comparison, The second element, S region, we use yellow color. Second element, 8 greater than the pivot, so we need to put it in the L region. So here I use the green color. So you see, we grow these two regions using different colors to mark them. Third comparison, next element, 7 greater than 4, put it in L region in green color. Comparison number 4, 1 less than pivot, so we should color it in yellow, but this time you can see the two yellow elements are separated by the green region. That's not good, because we want to put all the elements in the same category in consecutive locations, not separate locations. So we need to do some operation adjustment. What kind of operation adjustment to change the locations? This time we need to do the swap operation, appropriate swap operation to make it happen. All right, swap element 8 and element 1. After this swap, you can see that, because the order is not important, right? Yeah. The specific order of the data in each subarray is not important. So we do swap operation to make their locations of data in same category occupy consecutive locations. Yeah, we'll make it happen. That next operation, comparison, compare 3 and pivot. 3 less than the pivot, so we should put in the S region in yellow color. We need to do that swap another time. So swap element 7 and element 3, then we can organize the data in these two categories in a neat way. Yeah. Next comparison, 5 and 4, 5 in green color, no swap, right? Yeah. So in green color, we don't need to do swap. In yellow color, we need a swap operation. Yeah. But there is a last step. The last step, we need to put a pivot element in place, right? Yeah. Yeah. Pivot element. Yeah. So I will finish. Last step, we put a pivot element in place, then we're done. Okay? So another swap on this pivot element with element 8. Yeah. After that swap, you can see the pivot element is in place. Then the data is separated in two regions, left subarray, right subarray, and they satisfy the desired properties. See how smart it is. Okay? Yeah. Implementation, pretty straightforward. Yeah. Pretty simple. Yeah. But after all the analysis work, you can see we complete this important device step. All right, so let me stop right here. Next time I will complete the remaining part of part D. Then after that, I will start module 5, our last module of this class.